Hi, and welcome to Persistent Worlds, Managing Player and World State. My name is Benoit Gagnon. I'm a senior software developer at Unity Montreal. Persistent World is an emerging type of online experience, so multiplayer games mostly, and it distinguishes itself from other multiplayer experiences in the fact that it's long-lasting. And so there isn't really a defined start and end state for the experience, and just visitors come and go. And what visitors do in this experience, this persistent world, is they evolve their characters or the state of the world itself. And so this genre really dates back all the way to the MUDs, the early MUDs, and then through the golden age of MMOs. But recently, we've seen a resurgence of these kinds of experiences with genres such as world building or survival games, where players have an impact on the world. And in some cases, impacting that world or shaping that world is the core gameplay mechanic, for example, with Minecraft. And so this talk will be focused on the management of state with this world. So both the character, the player, as well as the world itself. Now, there are many pieces of data involved in the multiplayer experience, and some of them fall in what I call the game platform services category. So things like leaderboards, management of friendships, the presence of players, the economy in your game, seasons and events, profiles, and analytics. This is not the focus of this talk, but if you're interested in these services, I encourage you to check out these two other sessions during this Unite conference, which are going to touch on those services. So today we'll be focusing mostly on the state management that is core to the gameplay mechanics of the persistent world experience. So our agenda today will be an intro level session. We'll be looking at the classification and representation of the state, some architecture decisions regarding the multiplayer topology, the services that Unity offers, as well as a few key third-party offerings. We'll look at the impacts on your game server internals, and then we'll wrap up. And so first, let's try to come up with some classification of state. I see this as a spectrum ranging from the player state, going through the character state, and all the way to the world state. And as we move from the left to the right, this tends to be a lot more game specific. And on the far left, it's a lot easier to reason about these things in a generic fashion, and sometimes in a way that we can find services that just provide this as a service directly. And so in a typical online multiplayer experience related to persistent worlds, you have your players that are signing in, and then most games will allow them to create characters in the world, one or more. And so data that's associated with the player might be their preferences with the game, their achievements, with something more qualified to them, their profile, their friends, what groups and guilds they're part of, and what purchases they made in the game. Whereas the character becomes a little more specific to the game, and this is why we're moving to the right of that spectrum. So the inventory of that character, the quest log, the skill tree, etc. And finally, there's data that's sort of shared by all of the players in the world, and it's this state associated with the world itself. So items on the ground, buildings have been constructed, resources in that world, as well as things like dynamic terrain. And maybe sometimes dynamic terrain is a core sort of activity in the world to shape that terrain and assemble blocks and whatnots. This would also include data about your NPCs or wildlife, etc. And so as we go to the right, the challenges with dealing with that state are much more game specific, and also the services available to you to deal with this tend to be a lot more generic as a result, because they have to accommodate a wide variety of cases. So let's look at game server topology or multiplayer topologies in general. There's sort of two major kinds of multiplayer topologies. One is the dedicated game server, where, as its name suggests, a machine is dedicated to serving the game and running the simulation. Now, this machine can be more powerful than the individual clients. And so that's why this pattern is very common in persistent world experience, is that they tend to accommodate a lot of players. And so the performance of the central server is key to the experience of everyone involved. The other reason is just practical, because the server has to outlive any individual client, because there isn't a defined start and end period to the session. And so having that dedicated game server available at all times makes it much easier to deal with clients coming and going. On the other side, we have a particular kind of peer-to-peer architecture where one of the clients will take on extra responsibilities and serve as the host of the game, thereby running the simulation and acting as a server. So while that's also possible in certain cases, this talk will focus mostly on dedicated game server architecture, but rest assured that most of the services and techniques could apply to some extent to a client-hosted architecture. But in that case, you have to deal with issues like host migration when that client host goes away, as well as handling the scalability of that host. The performance of that host is going to be very impactful on the game. Next up, we have the authority on that state. And so introducing this game server into the mix, we've got a client, a game server in that whatever state database or service we're using, which gives us three options for authority over that state. It's very similar to just multiplayer state authority management in general. Either the client accesses the state directly and has full read and write access to it, or the server has exclusive access to the state, and the client only experiences the changes to that state through the gameplay itself. And finally, you can have a mix of the two with a shared authority, where perhaps the client has access to some of the state, the player state, the character state, for example, whereas the game server is the authority on the world state. Now, it could be a separation of the state. It could also be a separation in access control. So perhaps the client has read-only access to the state, whereas the server has full read-write access. And so it's important to reason about those things and decide ahead of time for each type of state in the game, because it will impact things like scalability requirements on your state backend. It will impact the latency and the costs involved with the networking over that state. But also, it will impact the choice of authentication parameters that you'll require from the client and the server. So the security aspects and sort of anti-cheat prevention. Now that you've classified the state, we have to consider the representation of that data at runtime. And so taking Unity game engine specifically, there's sort of two broad categories of projects out there. The traditional kind with game objects and mono behaviors and components, where the runtime representation would require some form of marshalling to an alternative representation. And probably the most popular one would be JSON here. And so some of the attributes on those components, some of the properties, a subset of them would be considered persistent state, and that's what you're looking to persist. Either the game objects and the components themselves, or data structures that are reachable from those game objects and components. In the second kind, we have the data-oriented tech stack, where you have entities and component, but the difference here is that the in-memory representation of that data is actually compatible with an on-disk representation. And so that's one of the core functionalities of the data-oriented tech stack, is that it packs the data very nicely to be the most efficient at runtime. But as a result, it's also very efficient for offloading and reloading into memory. And so that gives you an extra opportunity to represent your state just as any other entity's components and use the serialization format in its native form. Going back to the more traditional approach, a very naive but perfectly valid way to start would be to look at the built-in JSON utility facility, which lets you serialize objects, including mono behaviors, groups of logics, or any structure you have in your code base. Run that through JSON utility, which will produce some JSON document out of it. Now, if you pair that with a state storage system that accepts arbitrary JSON, you have a pretty good starting point for managing your persistent state. You do have to identify those objects that need to be persisted, and you'll have to define some sort of indexing mechanism, primary key to retrieve them. But in terms of getting started, this is a completely valid way to start. It's probably the first step along the way. Also, JSON utilities performance is really good. And so in the category of JSON serialization, that's a very good solid choice to begin with. Moving to a little more advanced consideration would be the spatial indexing. And so if the persistent world comprises a very large world map, which is often the case in these kinds of games or experiences, one strategy to split that memory, that map into multiple cells, grid cells, and so that the server can dynamically load and upload subscenes into the world as players move around. And so this is particularly relevant in the DOTS architecture because it's a common pattern for achieving very large world maps through subscene loading. And so to learn more about that part, check out the V-Rising session, which touches on that. But this is for the asset loading and sort of limiting the amount of assets loaded in the server memory to run the simulation. But the same technique also applies to the state management. And so if players can only affect state in certain grid cells at any given time, spinning up the world state in those grid cells and loading dynamically those cells have been mutated and serializing them back to persistent storage might be a very good way to couple the two systems and have the ability to do spatial indexing of your world state, which comes in very handy to reduce the data that's floating or that's flowing around between the game server and the world state persistent database. Now, looking at specific services that can store state, abstracting the persistence of data goes back a long way in Unity, and one of the first occurrences of that might have been PlayerPrefs. Now, PlayerPrefs is just a key value abstraction interface, and the data is going to be stored locally on your device. So it's not going to roam around if the player connects from another device, and it's also certainly not reachable from the game server or any other player in the game. So as its name suggests, it's for player preferences, user preferences, and you should only use those for that. But the reason I mentioned PlayerPref is that CloudSave in some shape is an evolution of that, where instead of being local, now can be stored in the cloud. And so this data now has the ability to follow the player to its authentication and be reachable from any device. On top of that, the key value interface has been enriched, and now the values themselves can be arbitrary JSON documents. You also have the ability to store a lot more data, and you gain the ability to explore the data from the Data Explorer on Udash. So as a developer, you can inspect the data for your players and debug issues and even fix them. Now, recently, CloudSave also added the ability to authenticate to it as a service account. So one thing to keep in mind is that the CloudSave data is always player scope. So it has to be attached to some player. Now, with the game server in the mix, you have the choice of still managing player-specific data, which could range from player data to character data, perhaps, but do that from the confines of the game server, as opposed to having your player directly contact that service. So a single game server can now essentially impersonate any player within that game and manage the CloudSave data associated with that player. And that's a very powerful pattern, because now the game server can have full authority on that data and just simplify the synchronization with the simulation of the world, the players, and the persistence of it. Now, one caveat is that today access control options are limited on that front. And so even though the game server is reading and writing that data, it doesn't prevent the player theoretically from reading and writing their own data. This is something the team is working on, and so we'll have more to share on that. Another service I wanted to mention is remote config, and mostly because it's often misused. And so remote config is a form of remote storage that is project bound and is the ability to serve data to your game at runtime to drive behavior or certain settings and control that remotely as a developer. Although it's project bound, this is not a great place to store world state. And the reason for that is that the data is going to be for the entire project. And so you can do segmentation with remote config, but this is for the case of A/B testing or rolling out campaigns and changing parameters for different audiences. And so it's best to think about data in remote config as data that would be mostly static and read-only, and use it very seldomly for data that you would update. And so this is not data that a game server or a game client would be able to write typically. Still, it's worth considering because it's a very powerful mechanism to alter the behavior of your game in a remote fashion and experiment with different values. Another very popular model is to use so-called file-based cloud storage or blob or object storage. You probably know them as Amazon S3 or Google GCS or Azure Blob Storage. This model lets you write arbitrary byte streams, essentially, with file-like semantics. And so files become objects and folders become buckets, and you can set ACLs and policies on those. But the idea here is that you can essentially store anything you want and invent your own file format. This can be text, it could be binary, so a JSON document stored as an S3 object or a GCS object would be a completely valid way to go. Binary, it could be that dots on disk representation might be a good place to start. Or you can invent your own, game save format and tweak it so that it has the absolute best performance and compact features that you need. The downside of this approach is that the upload and download is optimized to be done atomically. And by that, I mean that you either upload the entire object or download the entire object, and you replace the entire object, but it's not optimized for partial random reads and writes. Also, the latency to the first byte is going to be very high. And so it's not a replacement for a database. It's more a substitute for a file system that may be volatile or ephemeral. With this approach, you can make it a little more persistent. Still, very valid way to look at persistence if you want full freedom. You can also split into multiple files with different kinds of state and do any kind of segmentation and indexing that you require. Next up is the very vast world of distributed databases. And so a distributed database would be qualified as distributed due to the fact that it's accessible over the network. And so traditionally, this was the world of relational databases. And although those are still around, they sort of have grown out of style in many cases due to this renaissance of database technology over the last few years. And so MMOs, for example, were heavy users of relational databases with complex transactions and multiple tables. It's still a perfectly valid choice. If you can reason about your game's mechanics and design in a relational manner, and you can define those strict schemas and deal with the evolution of that schema, you'll find plenty of managed offerings for relational databases or run your own. So they're available in all major clouds. However, what we're seeing more and more is that people are turning to the so-called non-relational distributed databases or NoSQL offerings. And so it's kind of hard to define that as a group because it defines itself as the absence of something. But still, we see categories emerge out of that in terms of document stores and key value stores being the two primary ones that we see the most. Key value stores are often used as caches, and so not as the primary stores, but a secondary store that has lower latency, and then combined with a more durable storage, be it a relational or a document store. That being said, for the most part, we're seeing a lot of interest in document stores, which is that ability to reason about your object as just structured documents, for example, JSON, and do a key retrieval of those entire documents. And so of those, Mongo, Firestore, Firebase, and Dynamo are the ones that come out the most. So the benefits of distributed databases, obviously the access anywhere, being on the network and internet facing, you'll be able to access that data everywhere. It also, the fact that it's on the network makes it very interoperable because this makes it very easy to port the drivers to different programming language. And so from different runtimes, you'll be able to access that data. The fact that the data is stored off of the game server makes it durable, and the replication features can also increase that durability furthermore. And it's just more scalable in general. Modern databases will scale linearly beyond the capacity of a single server. So you have massive amounts of data to store. Distributed databases are the way to go. And finally, they're highly optimized for high concurrency. And so you can have as many game clients talk to them or game servers talk to them concurrently. They'll scale very nicely for that. However, of course, this comes with a lot of challenges. The fact that it's on the network means that you have to deal with the bandwidth and the latency involved with that network connection. And the other category of challenges is in the capacity planning and operations. So how big are you going to make that database cluster, and who's going to run the upgrades and the backups and the maintenance? There's a lot of hidden complexity there, especially if you haven't run distributed database at scale before. So a lot of pitfalls in running those big databases, which leads to managed database offerings. So from cloud vendors or from the database vendors themselves, which sort of liberate you from some of the operational complexity and gives you a lot more flexibility in terms of scaling. So of those, we identify Atlas from Mongo, which is the managed MongoDB offering, Google Firestore and DynamoDB as sort of the top contenders for managed document stores. Depending on which store you want to deploy to, which cloud you want to deploy to, you might pick one over the other, with Atlas being the more flexible because it will deploy to any major cloud and not being tied to any specific one. Moving on to the internals of the game server itself, we have to account for the fact that a game server typically runs at a fixed tick rate. And so common values might be 30 hertz or 60 hertz or even higher for competitive shooters. And so all of that simulation happens on a fixed rate, and the operations have to fit within a certain time budget. Just like on the game client, you have a budget to render your frame, you have the same thing on the game server. And the issue is now we're bringing a new component that has variable latency to it. And so we have to account for that latency in the simulation loop now. The first kind of latency is network. So obviously, if the game server is now far away from a database, which adds, let's say, an extra 100 millisecond, if the player was already 100 milliseconds away from the game server, performs an operation against the game server that has to relay that operation to the database and come back, you're looking at a much higher latency. And so this is why we typically try to reduce the latency between the game server and the database as much as possible. For the same reason, we try to reduce the latency between the player and the game server. But we tend to have even more strict tolerance for the game server database network leg. Even if you manage to reduce that latency to sub-millisecond, because it's the game server and the database are co-located in the same region, same data center, same rack even, or same machine, you still have to handle the transaction latency. And so operations against a database, particularly a very loaded one, will take some time. They're not instant. And so that transaction, because the database has to guarantee durability and that the transaction goes through correctly, there's an inherent latency to that transaction. And so the player calling some form of update world function, the game server has to make that transaction to the database and wait for the reply before returning OK. Which leads to various strategies for compensating for that latency. And so if you're familiar with multiplayer game networking, this is not unheard of. You've been doing this for many things with your multiplayer game. And so the technique of, for example, optimistically returning the result to the player, even though you haven't received confirmation from the database, is a very popular one. It can be very valid in many cases. And so this sequential approach, for example, would put all your database operations on a secondary thread, and you could sort of accumulate changes you intend to persist to the database without blocking the replies or the impact on the simulation. And so this accumulation in the background eventually will get committed to the database, but for the most part, the game goes on without receiving confirmation. It's a little more challenging if you don't have access to the full data set inside the game server. And so if state is only available in that database and the simulation is waiting on that, you'll have to account for that no matter what. Which leads to a second approach, which is concurrent. So you have operations against a database of various duration, and they can sort of overlap each other and taking advantage of the concurrency features of the database itself. Now, this is also harder to reason with because you've got these pending things going on in the background, and the results can come back at any time and somehow incorporate that into the tick rate. And finally, there's the synchronous approach. So if you can manage to make the database operations short enough that they can be included as part of the network tick, you don't have to deal for that case where the database operation exceeds the time budget you have for a single network tick. And so doing that would require a very fast database. It would require a very predictable database, and one that probably has no network latency at all. Which leads to an interesting option of embedded databases. And so an embedded database is really a full-featured database that's co-located with your game server. And so it's really more like a library that you link into your game engine or game server process. And the interactions with the database are purely function calls. And so the actual data is stored either on disk or kept in memory, but you get the same semantics of the database without the cost of network access and this variation that comes from a highly concurrent database. So of course, the most widely used example of this would be SQLite, which has been around for forever. And this is also a pattern that's been very popular for mobile app development for a very long time. So nothing new here. If you've used Core Data or its Android equivalent, embedded local databases that are part of the application is a very popular development model in those areas. The other reason for this model to be very popular is that it allows a seamless online-offline transition, in that when offline, you still have full database semantics over local data. Now, of course, offline with the game server doesn't really apply, but the interesting novelty here might be to apply the same design pattern to the game server itself. So if the game server is equipped with an embedded database, it can sort of guarantee certain performance characteristics for its data, and then the game clients in turn will benefit from that reduced latency and predictable performance. And so benefits, of course, the very low latency I mentioned. Now your interactions with the database are really just function calls, which are orders of magnitude faster than actual network calls. There's also much higher bandwidth here because you're essentially interacting with the disk or even in the memory in some cases, which means very predictable and fast IOPS. You're approaching SSD speeds essentially, which unlocks a ton of possibilities in terms of how much data you can pull in and out within a single tick or over a series of ticks. The compute is shared with the game server, so essentially the database server is already paid for. There are no extra costs for that database. There are also no idle costs, so data that's not needed right now, not attached to any game server, doesn't cost anything in terms of storage. It costs only in storage and nothing in terms of compute or RAM. And then there's just like a ton of convenience features for it. The debugging is much easier because an embedded database really is just a file on disk. It has file semantics. It can be treated as a single file for all intents and purposes. So it's very easy to download a file, inspect it, patch it, and re-upload it. Compared to the very involved snapshot and restore procedure of distributed databases, particularly those that are sharded and distributed over multiple nodes. And finally, simplifies the security and authentication because the access is through function calls to a local file on disk. So authenticating to your database is a non-issue, really. Now, of course, this comes with some challenges. First off would be the limited size. You can only store as much data as the local disk will allow. So this caps the total amount of data you can store in that database. As well as the durability, the data is only as durable as the host itself, which will force you to define a solution for long-term storage and long-term durability. The other challenge is that this access to this data requires the database engine library to be attached to it. So it's a little less flexible when it comes to accessing this data in context other than the game server where that code is sort of tightly coupled. Finally, concurrency is limited, of course, because these databases are designed to be accessed only by local processes, and so they're not meant to serve hundreds or thousands of clients concurrently. And the analytics of those databases, you're going to have to essentially open up each database individually and run the queries there. So more challenges on that front for sure. Now, I'm happy to report that this is an area we're investing in. And so Unity roaming databases, named TBD, but is something we're working on, which will allow you to have roaming embedded databases that follow the game server and are ready to use as your game server allocation starts up, which will give you the functionality of databases with transactions and a rich SDK without some of the pitfalls of those large systems. We're also making it very cost effective because the only extra cost will be in the form of storage and transfer of that database in and out. It also opens up new possibilities, for example, by cloning and forking those database files and create complete new instances of a world state, which can open up some new gameplay ideas. Snapshotting is going to be a core component of this. So the ability to snapshot a consistent version of a world state and roll back to that, either because the gameplay needs it, or because as a developer you want to do some customer support and fix an issue. And finally, because we have that opportunity, we can make it interoperable with other contexts and sort of alleviate that problem of embedded databases where the whatever process produced the data is the only way to get that data back. So we can free that data up and make it available, for example, in other contexts like cloud code functions. And finally, it's just going to be very developer friendly in the sense that you can get started without signing up for any cloud services. At the end of the day, it's a file on disk and some library. And so there's really no cost to get started with embedded database. So stay tuned and contact us for early access. So with that, I'd like to recap. We've looked at different kinds of state. We've defined different models for managing the authority over that state. Briefly looked at serialization strategies, with JSON probably being your best bet if you're in the vast majority of cases, and DOT's built-in serialization, built-in world serialization might be another option. We looked at some of the storage services, and rest assured that Unity is investing in sort of database as a service and storage offerings in general. So we'll have more to share about that in the near future. And finally, we looked at the impacts in integrating those higher latency services into a simulation loop. So with that, I thank you very much, and I invite you to get in touch if you're working on a persistent world game or non-game project. You can reach us at this email address here. So thank you very much.